So in the previous segment we stopped at this point saying that we will take up this topic of again perception only. That means when we say something is loud, we not only talk about the intensity, we also talk about the frequency, because we said that A weighting and all, right. So some frequencies are not so perceived as very loud. So these are the curves which tell us, that thing. So they have conducted a lot of experiments on healthy human beings, and then came up with these pictures, curves. What they tell you is very important to know and understand. Loudness, they are called loudness levels, and they are represented with, or the unit of that is phones. Okay. Now at 1000 hertz, where actually our ears are most sensitive, it is considered at least to be that. So if you hear a sound of a given frequency, okay, 1000 hertz, it is conventionally taken as the same sound you are perceiving. Your perception and the actual sound are same. That is why the A weighted was having zero correction there. Okay. So that means a 20 dB sound will be heard as 20 dB sound. A 30 dB sound will be perceived as a 30 dB sound. So like that. So that means if you so 30 dB if you go here, so it will match there. But then if you come down in the frequency at 500 hertz, the perception of the same loudness, if you are trying to achieve, you will go to say here around 40 dB. So if you go to 40 dB sound at 500 hertz, you will have the similar feeling or perception as that of 30 dB at 1000 hertz. So these are those curves, means equal loudness curves. That means if you say 50, it is the curve on which a person feels equal loudness what he or she was feeling at 1000 hertz. Okay. So that's the full picture of our sensitivity with respect to frequency and amplitudes and everything. So when we say loud, this whole thing actually plays a role. It's not just the intensity. Okay. And then there are two things. One is this phones through which we can describe the loudness levels, and there is one more index which is called zones, which is the loudness index. Okay. So I'll just in a minute I'll tell you what is the relationship between zones and phones. Now anywhere, anytime you measure something, based on these indexes you pick these numbers, and there are some relationship to convert from zones to phones to tell that what is the equivalent loudness level at which you are hearing something. So keep this in mind, and then I'll just show you the formula for now the relationship between the zone and phones are like that. S is equal to 2 raised to a level in phone minus 40 divided by 10, or you can write phone as 40 plus 33.3 log of S. And S total you can calculate like this: S max plus B. So these are all empirical, okay. Summation of all SI's over all I's, okay. And B is equal to 0.3 for 1 octave and is 0.15 for 1/3 octave. And in this summation you do not add this maximum. Now what it means, I'll just tell you now. Suppose you have measured some sound signature, okay, say at 63 hertz octave center frequency, then say 120, 250, like that. In every octave band you have measured some sound. Then using that, suppose this is a you have measured 68 dB, here you have measured say 75 dB, here you have measured say 90 dB, okay. Now you have to, so 68, 75, 80. Now if you go to that picture, so 63 octave center frequency, so you had what, 68, no? Now if you go to 68, so it's almost like 2. The index, the loudness index in sounds is around 2. So that SI for that is 2. Similarly for, what was the next one, 70 or whatever. So then 125 hertz, 70 dB, again you have to calculate that SI, and like that you just add them. But then when you add, you must not add the maximum, the band for which you have got the maximum source value. So that you have to keep it out of that summation, and all other things you have to add and multiply with this factor. And here we were seeing octave bands, not 1/3 octave band, so B will be 0.3. So like that you just have to get this value as total and put it here to get the phone value. So that will give you the loudness of the sound as a whole, okay. So because at every frequency there was some energy content. It is not that all the energy was concentrated or at a single frequency. So the equivalent loudness which now you will hear or you will perceive is that which you will get from this, okay. So that was about yeah, in a way, yeah, that's fine. How to get the perceived loudness. And one more topic I should club into this is about, because here we are doing a similar thing, is about adding the levels, right. When you say that, suppose there is a fan which is making say 70 dB sound at your location. Now you switch on another fan which is also at similar distances. Now how much sound you will have at the location of concern? So you will have to add SPLs, right. So you just don't add SPLs like 60 dB plus 60 dB is 120 dB, because they are in log scale. So the idea is you have to always convert them into the energies, add the energies and get back to the levels. So if you do that, the formula for adding say sound power level is like, you know, so 10 log to base 10 of summation 10 raised to 0.1 LWIs for all i's, whatever. Fine. So basically this term does nothing but calculating the energy. Okay, for ith source LW, it is calculating the energy. Then you are summing up all the energies from all the n sources and then doing again the same thing. Then similarly for sound pressure level, what would be the formula? Any guess? If you remember the sound pressure levels, how you define sound pressure level, LP was 20 log P RMS over P reference RMS. So that is how you had done. So that is how you had defined the sound pressure level. So what should be the thing here? Just think a moment. It's exactly the same formula. Right? Because this you can't just divide by 20 and take when this 1 over 20, 10 raised to that, you can't just add them like that, because then what you will do is you will sum these terms. P RMSs you will sum, but they are not representing energy, they are representing pressure. So their square actually will represent energy. So that is why here also when calculating or adding sound pressure levels, you have to convert them into energy. That means this 2 which is sitting here has come from its square, right? P's square, which is actually energy. So that you have to take there back, so that then these term will represent energy, and then again you do the same thing. So that is why this here again still it is 0.1 only, it's not 1 over 20. Okay. So if you just remember that, okay, I had to add energy, then there will be no issue. Anytime you do, you don't have to remember this thing. So it's if you know what's the sound pressure level or sound intensity level, you can always do that. Okay, and now this is about adding different sound sources at a given location. But what about something called, average over a whole day they take? Suppose traffic noise, it's varies over whole day. So what they do is they average it over every hour or something, and then over full day it's again averaged. So that formula sometimes you can just write it down. Say this is 8-hour average. If you say only the daytime, so you write as 10 log of 1 over 8 summation of 10 raised to 0.1 LWI. I is from 1 to 8. Okay. Now here why I wanted to make this point is, here you are dividing by this 1 over 8. So there you are not. The reason being, there you are adding all the energies at a given location. Here you are averaging over these times. These i's are representing at different times over 8 hours. Okay. So over that 8 hours you measured that LW, and then so you can't just add those energies because they were at different times. So that is why you have to average them. So that's how it is done. And there is a other 24-hour formula. I'll just, for completeness I am writing, you don't have to remember something. 24 hours. So that will be 10 log 1/24. So 15 times log, sorry, not log, 10, right? 10 to 0.1 LWI plus 8 into 10 0.1. These are not i's, these are in fact these are LW. So I'll say this is day, this is night. So here I have to write not that. Sorry for that. Here I need some space also. Here 10 raised to, it will become 0.1 LW night plus 10, and here also it's not 8, it's 9. Yeah. Okay. So that is how you calculate, means over the day from 6 a.m. to 9 p.m. So this is the average on that, it's the day average, and that you weight with a 15 factor, and the night one you average it with a weighting factor of 9, but there is an addition of 10 because perception wise in the night we feel more annoyed at the same loudness. So that's why this 10 has been added, and then you just divide by 24. So that's the whole thing. Okay, so that's the day average sound pressure level. And some interesting facts one should always keep in mind that about these additions. One fact is, say 100 dB plus 100 dB is 103 dB. This addition is the SPL addition, that is the logarithmic addition. So if you add two sounds of equal sound pressure level, just 3 dB increment will happen. Okay, because log 2 basically is 0.3, so that 10 times 0.3 is 3. So from there that 3 dB is coming. Okay, and so if you go through that expression which you wrote now, you can again see the same thing, this one. So here if you put 100 and 100, you will get 103 here. Okay, so yeah, then what else? Then say 100 dB plus 90 dB is like 100.4 dB. That means when the difference is almost like 10 dB between them, the addition is only about 0.4 to the maximum one. Okay, the higher among them will just, if you add 0.4 to that, you will get that. Okay, and if it is, the difference is more than 10, also you can simply add that thing 0.4. Because I'll tell you that. Then let me tell it now. Here you just see this. There is a curve which can be used to add things, and they look so like this. Now this thing, the x-axis in this curve tells you that what is the difference between two sound sources, the SPL of two sound sources. Okay, LP1 minus LP2. Now this curve is telling you that how much you have to add to the higher value to get the summation. Now if the difference is 0, that means 100 to 100 you are adding, then you have to just add 3, that comes to 103. It is a quick curve to add things. Okay. Now if you are having 100 to 90, if you are adding, the difference is 10, so you just add 0.4 to this 100, you will get it. So at any other value you can just add that like that. 94 plus 100, so the difference is 6, so just 101 is the answer. So if you have such 4 sources now to add, so you just start from the lowest one, 80, 86, difference is 6, yeah, like this. So you just add 1 to the highest one, so 87, then 87, 93, what's the difference? Again 6, so 94, oh 94 to 100 again, so 6, so 101. So when you have all these 4 sounds together, your total sound pressure level will be 101 dB. Right? You could have done that using the formula which you saw there, but if this graph is there, it's handy to calculate, nothing else. Okay. Now, so this should tell you this interesting fact that adding 2 sources doesn't feel like doubling the sound. Okay. Just it adds 3 dB, and in fact the third point which I wanted to make is 3 dB increment, is what do I call, means what, okay, is hardly noticeable. So that means if you just switch on another source of the same power, hardly you will notice, because it will increase only 3 dB. So if you can go beyond 5 or 6 dB, then it's perceivable. Okay, if the sound increment now becomes 5 to 6 dB, so then it will become perceivable. And one more fact, interesting fact is, if you have 10 identical sources of x dB each, then you will have a sound pressure of x plus 10 dB. Means, for example, in the orchestras, they have say 10 violinists, each one is producing say 60 dB. So together they will produce 70 dB sound. Okay, and if you remember, I had told you in a segment that when we increase the loudness or perceived loudness equally, the intensities go in like logarithmic way. Here we are just, every, in a way, for 10 identical sources we added and 10 dB we added. That means 1 dB was equivalent to that 10 raised to 1 over 10, you remember? So that intensity increment was added by each of them. So the first one, when you added, it becomes 10 raised to 1 over 10 times the main intensity, the original intensity. Then the next time when you add it, it becomes 10 raised to 2 over 10, 1 over 10. So like that it goes on. And then this increment was in fact termed as dB, 1 decibel of increment of sound. And that's how the full one, when you increase, 1 bell of increment. Okay. So that's the thing. Any other? And then one more thing. This 10 dB increment, when it happens, we feel as if the sound has doubled. When we say we perceived the sound to be doubled, actually a 10 dB increment has happened. That means when 10 violinists play, you will feel as if the sound has doubled as that of a single violinist in an orchestra. So that's the whole thing. Okay. And so think about what if we add another 10 violinists. Think about it. Will it add 10 dB more or? Okay. So that's the whole of the thing which I wanted to talk about. Sound intensities, sound perceived intensities, sound pressure level, sound intensity level, frequency bands, because we talked about octave bands and 1/3 octave bands, and weighting of the frequency bands. So this is in a way a general knowledge about sound which everybody should know and remember also. The rest of the things you can forget after some time. The expressions, the formulas which we have derived or we will derive, but these are the things which should be in your mind. Okay. So, we will stop here for this segment and we will see in the next segment.